So to begin with, melanoma still remains the most lethal form of skin cancer today. With the increasing power of machine learning, the early diagnosis of melanoma has begun to shift from solely expert dermatological evaluation to including automation as well. In any machine learning context, there will be inherent biases according to the nature of the training data set, whether it be class imbalances between different forms of dermatological lesions or the stage of development at which the pictures are taken. This will surely impact the predictive and diagnostic power of the model. So the problem our group set out to address was the imbalance in skin tones found in one of the most widely used skin lesion data sets called HEM 10,000. While darker skin tones are considered to be less at risk for melanoma than their lighter counterparts, there remains an ethical and moral need to ensure that the AI systems are not disadvantaged at predicting the presence of melanoma in these underrepresented populations. So another limitation in these data sets is the paucity of melanoma data points. Predictive models are best optimized when working with large data sets. So that being said, for this project, we have utilized the power of unpaired image-to-image translation using a CycleGAN model architecture to generate synthetic multiracial melanoma lesion data. Thus, we hope to address the issues of data bias and data scarcity. And the model is based on the paper called Unpaired Image-to-Image Translation using cycle-consistent adversarial networks.
So before we get into our model architecture, we need to talk about the data that we used. The data we used was compiled from two data sets, one that we have mentioned before, the HAM 10,000, and then MR2 data set. This data set is a multiracial mega resolution database of facial stimuli created in collaboration with the psychologist Nina Strominger and Kurt Gray and the photographer Titus Brooks Hegan. The data set contains 74 full color images of men and women of Europe, African, and East Asian descent. The data set was then pre-processed and augmented via TensorFlow's data augmentation pipeline, which then provided us 3 sets of varying skin pigment saturations. This made our data set more robust, as 74 images is not as strong as that we needed, so we wanted to increase that amount. The facial images were then cropped into a 256 by 256 pixel image of the forehead portion of the person or individual's face. They decided to use the forehead area because it gave us a smooth skin surface, absent of hair and absent of strong facial features. The second data set, as mentioned, is the HAM 10,000 data set, which contains 1,113 malignant skin lesions. This data set had supplementary metadata that identified the actual skin lesion type on the image, which was also parsed in with these images. And then finally, these were also normalized and reshaped similar to the MR2 data set into 256 by 256 images.
As mentioned earlier, this project incorporates a CycleGAN model architecture, which is an extension of generative adversarial network GANs, and it also builds on the Pix-to-Pix framework. The general idea behind unpaired image-to-image translation is to relate two data domains, X and Y. In our case, domain X represents the synthetic skin tone data, and domain Y represents the melanoma data. Our architecture involves feeding in the skin tone data and the melanoma lesion data, and with the use of generators and discriminators, predict how the lesion would appear on the input skin tone data. The generator used in this model is a modified UNet, which features an encoder that downsamples the images and a decoder that upsamples them. In each block of an encoder, there is a convolutional layer, a batch normalization step, followed by a leaky ReLU. For the decoder portion, there is a transpose convolution, a batch normalization, and a dropout before applying ReLU. The UNet generator also features skip connections to ensure the proper flow of gradients during backpropagation. Lastly, since our goal was to generate synthetic skin lesions on an arbitrary given skin tone, it was crucial that the resulted image and the original skin tone image shared a certain level of structural similarity. And in order to assess the robustness of the predicted images, we use the concept of structural similarity index scores, which essentially is computed by taking into account luminance, contrast, and structural similarity of the images. And due to the medical nature of this project, we wanted to ensure image quality was maintained and that SSIM could be used as a proxy for the recapitulation of skin tone into predicted images.
So moving on to the loss function, again, to reiterate, the idea of a CycleGAN is to use these unpaired image-to-image translation. And so in order to enforce that the input and target have a meaningful relationship during training, there's this idea of cycle consistency loss, which is really the hallmark of a CycleGAN. Cycle consistency ensures that the resulting image, predicted image, should be close to the original input. And so in our application, cycle consistency must be fine-tuned because our hypothesis was that having no cycle consistency would make the model have no reason to generate a new skin tone. But conversely, too much weight on cycle consistency would preclude any adequate melanoma skin lesion generation. And so for this reason, one of the main adjustments in our model was the fine-tuning of the lambda hyperparameter, which was the value that controlled the weight of the cycle consistency loss during the training. And so we used a variety of lambda parameters ranging from 0 to 20 to qualitatively and quantitatively assess the differences in predictions. And so now kind of discussing about the results, you can see in the table some of the different structural similarity index measures for a given sample. So this was for one given sample skin tone, the various SSIM measurements for lambda. And quantitatively, the lambda which achieved the best performance was 10. However, one of the issues that we faced was that the variety and diversity of output predicted images was somewhat limited, and we hypothesized that we might have faced the phenomenon of mode collapse, which is common in training generalized adversarial networks. And so moving on, the various challenges that we encountered through this project, in reflecting on this project, there was a lot of computationally heavy code which precluded us from fully training the model to the full number of epochs that we would like to, given all computational resources.
Lastly, it is still uncertain whether this model is the ideal candidate for addressing the issue of skin tone bias in dermatological lesions datasets. We hope that future work can build upon our research with more intensive computational power and generate even higher resolution synthetic images. Furthermore, another limitation was the source of data. A promising future direction could be for clinical clinicians and ML researchers to create a larger and more diverse data set of melanoma at various stages and skin tones respectively to aid in the continual process of debiasing skin lesion data sets.
Thank you all for.
Thank you very much for listening.
Thank you.